We often treat spontaneous brain activity as a collection of random, localized electrical events, isolated flickers of energy occurring within the three-dimensional container of the skull. Magnetoencephalographic evidence at the millisecond scale reveals a different reality. High-resolution MEG scans show that cortical activity is not point-local noise, but a continuous, highly structured propagation field. Across hundreds of subjects, the human cortex exhibits a massive anisotropic broadband flow. This activity is biased heavily along a specific axis, moving from the posterior sensory regions toward the anterior association cortex. This flow maps precisely onto the brain's folded 2D surface. Treating the cortex as a Riemannian manifold rather than a 3D volume, we see activity moving as a fluid vector field, following the path of least resistance across the physical topography. Standard neurophysiology describes this movement as a sequence of temporal events, a signal or physical substance traveling across a 3D space as time elapses. However, describing activity as a manifold flow creates a mathematical tension. If the most accurate description of brain function is a 2D geometric flow rather than a 3D volume event, the physical brain might not be the primary container for these dynamics. We need a framework that treats the geometry of the surface as the primary observable. The TCGS-SEQUENTION framework resolves this tension by moving beyond the container ontology of a 3D brain. Under this lens, the biological cortex is a shadow manifold catching projections from a 4D source geometry. The flowing activity is a shadow cast onto this map. A formal pullback equation dictates this relationship, deriving every measurement from a deeper four-dimensional content field. In this model, what we measure as time on an MEG scan is a foliation label, a gauge parameter used to organize our observations, rather than an independent physical variable. This places the true source of cortical activity in a timeless counterspace. This 4D geometry is static, whole, and contains every admissible brain configuration simultaneously. Recording these directional brain flows is the first step in mapping the hidden, static geometry of that 4D source. We are surveying the territory by analyzing the shadows it leaves behind. To build a map of the source, we have to look closer at the specific frequencies rippling across the cortex. The MEG data shows different wave frequencies occupy the same cortical space but move in opposite directions. Slow waves move upstream toward association regions, while beta waves move downstream toward sensory regions. The standard model interprets this as bidirectional signaling, a physical collision of bottom-up sensory data and top-down cognitive feedback. The framework identifies these as layered projection modes, complementary occupations of the same structural corridor, projected from a single counterspace geometry. These sheets represent distinct spectral channels of the same pullback. On the biological shadow, this mimics bidirectional traffic, though the source remains unified. An admissibility constraint governs this behavior, a geometric rule dictating which directional flows the shadow manifold inherits from the corridor. Bidirectional propagation acts as evidence of a unified topological corridor. We are observing the stable occupancy of a 4D structure, rather than competing brain states evolving in time. In the context of cortical flow, kinetic energy is measured as the squared magnitude of the tangent flow vector on the manifold. The data shows a sharp spatial gradient. Kinetic energy is highest in the posterior sensory cortex and dissipates as it moves toward the anterior association cortex. While it is tempting to view this as a literal reservoir of biological fuel being depleted, the mathematics suggests a different reading. Within the framework, kinetic energy is a functional shadow signature. It indexes local admissibility strength, the intensity with which the shadow pulls from the source. Rapidly varying propagation in sensory regions indicates a high gradient pullback, whereas the stable, low kinetic regions reflect a more balanced occupation of the corridor. This maps directly to human behavior. Individuals with higher kinetic energy in their frontoparietal networks exhibit higher scores in fluid intelligence. Cognitive capacity and fluid intelligence are expressions of effective projection strength through a geometric corridor. They track the local geometry of the source rather than the metabolic efficiency of biological machinery. By analyzing these kinetic energy series, we can identify dwell times, moments where propagation strength reaches a minimum and the cortical state stabilizes. These dwell times grow systematically longer as activity moves into the anterior association cortex, where complex integration takes place. Standard neuroscience assumes that more time is physically elapsing in these regions to facilitate thought. Within this framework, persistence reveals itself as spatial thickness, a physical depth within the source structure. This depth is what we measure as intrinsic neuronal timescales. The longer a state appears to last, the deeper the geometric column is within the timeless counterspace. These temporal pauses are cartographic measurements. They gauge physical thickness by observing projection stability. As the biological system matures, the way it registers the counterspace begins to shift. Lifespan data shows that as humans age, the proportion of slow upstream waves decreases, while beta downstream waves increase. This is frequently interpreted as a sign of decay, the sensory failure or physical degradation of the brain's internal wiring. The framework identifies a biological filter, labeled K-FES, that maps the total content of the counterspace onto the accessible shadow. Aging is a systematic reweighting of these projection modes, a process of filter retuning. As the biological filter shifts its configuration, the shadow transitions from a slow wave bias to a beta wave bias, while the 4D source remains unchanged. The corridor geometry of the counterspace is preserved. The territory remains intact, only the map reorganizes. This rebalancing of projection modes dispels the illusion of structural decay. It suggests that cognitive aging is a change in the filter, not the destruction of the source. Metrics like directional flow, kinetic energy, and dwell time act as spatial surveying tools. They index an underlying geometry that is usually hidden from view. The high-resolution Liu et al. Dataset provides the exact coordinates needed to map this topological reality at the level of human neurophysiology. We must now transition from analyzing the brain as a machine in motion to surveying it as a shadow manifold. The TCGS-SEQUENTION framework absorbs this neurophysiology without requiring changes to its existing axiom stack. By studying these electrical flows, we are not tracking events in time. We are mapping the permanent, timeless geometric